So, Vanakkam. So, we will continue our lecture on engineering seismology. So, last class we have been discussing a couple of classes about the interpretation of the earthquake records. Okay, so what are the time domain parameters, frequency domain parameters. Then we also seen how the frequency domain parameters will be useful to basically to get a simple theoretical model to verify the ground motion data how it's recorded. So, we have seen that basically the energy loss, the energy at source, energy at a site where it measured. So, how the energy losses you can count by taking a distance and the stiffness of the material into account. So, we have seen a simple point source model and planar source model. We also understand that these models are very easy to use, even a hand-made calculation or Excel will be sufficient. You can use cross verify the data recorded. Okay, so that is the application of these models. So, these models are extensively used in the geotechnical engineering, even though it has the assumption that materials are homogeneous and then uniform throughout the travelling path, but some extent these assumptions will help to get overcome. So, we have seen that the point source models are applicable up to the magnitude of 5. So, beyond that the planar source models are good. We also seen that both the model taking as a epicenter and hypocentral distance. So, we understand that the epicentral distance are more appropriate than the hypocentral distance. So, today class we are going to talk about some of the important parameters which we have discussed last time with a typical example such as a time history and response spectrum and tripartite plot. So, what it means, why it is very important, then followed by stochastic simulation models available in the simulating the earthquake data. So, how earthquake data can be simulated in the computer, what are the models are available. So, that we are going to discuss in the today class. So, as we have told that, so the earthquake data what we record is actually the acceleration time history or velocity time history. This is called as a time history data. The variation of the acceleration or velocity with respect to distance has been measured. So, you can see here basically. So, this is the typical earthquake record. So, for the 8 magnitude and 160 kilometer. So, you can see the this is predominantly the P wave S wave component. You can see how the S waves are various. So, as you know that you can pick up basically the peak points, so which is what is the value of that, and then you know how to estimate a duration also. So, these two parameters we can directly obtain from the here. So, you can pick up a peak points which may be acceleration or velocity and then displacement. In this case is the acceleration versus time. So, you can get a peak acceleration. You can also get a sustained acceleration, effective acceleration. So, those kind of things, and duration by fixing a threshold value of 0.01 and then converting to the OSID plot and then making that the energy plot, and then you can also get a significant and then the effective duration kind of parameters we can obtain from here. So, this is what you can see. So, you can also see these earthquakes are some of them are like very long duration, some of them are the short duration. This is you can also link with the kilometer distance which you used. For example, 8 magnitude, 160 and 198, you can see there is a long record. This is basically a larger duration record. So, similarly this is a 44 and 38, you can see that it is a short record, but the amplitudes are high. So, depends upon the site where you basically record the data, accordingly you will get basically your duration and amplitude into account. So, we have seen that basically. So, this is where the earthquake rupturing is taking place. For example, this is the rupture. So, this is the site. So, this is your recording station or your house kind of things. So, this waves what it does basically. So, it travels like this and reaches here. So, as I told you that, so any place you do not find the rock itself as a surface. So, you will have some kind of geologically weathered materials which is called as a soil, then followed by you will have a rock. then followed by your rock will keep on increasing with a different rock. So, this particular rock, okay, where the rupture is taking place, this is actually a focus. So, this is the focus and this is basically your epicentral distance, and yeah, this one is basically your hypocentral distance, and this is basically your H, depth of the earthquake. So, depends upon the composition of so this material and this path, what you are getting here, you will get a different amplitude, okay, and then a duration. Okay. So, which we have seen simulating a typical data we have seen. So, for example, if you have the similar setup here, okay, so this will be, you will have the different record. So, like this you will have the different record of the amplitude and duration for any earthquake. So, which you can understand that this variation not only with the distance, this also varies with the where you record. For example, this portion I will draw you in the detail. Okay. So, as I told that this is the surface, you will have the different layers. So, I am only the zoomed portion of the, so this portion basically this one I am drawing a next page. So, this is the bedrock, it is called as a engineering bedrock. So, why engineering bedrock? Basically here only the where the engineers rest their foundation, that is why it is engineering bedrock. So, this is called as a seismic bedrock, where basically the earthquake origins. Okay. So, this is engineering bedrock. Okay. So, this will have the 700 meter per second. So, this will have roughly 2500 meter per second of the Vs value generally. Okay. That is how it is defined. So, if you look at this portion, engineering bedrock portion, so if you look at this portion, we have seen that these waves are here, are we have seen it is with respect to the. So, the same wave when you go different depth, these waves are will be different, depends upon the basically the rho and Vs value, and then the like basically G and Young's modulus, which is again can be defined as the function of rho, Vs and Poisson ratio. That is what we have seen in the wave propagation. So, depends upon the this properties, basically you will get different waveform at a different level. So, this waveform what we are getting basically is directly recorded data. Okay. This is called as a time history data, which may be velocity is the velocity with the time or acceleration with the time. So, you can also measure with a different level. So, this is the time history based time domain parameters you can get from that. The response spectrum we have seen that it is a response of the single degree freedom system for a given earthquake. So, as we said that is the response of the given earthquake. So, obviously, here also this response what you are measuring depends upon the where you are measuring, the response will be different, because the given input you are getting the response, correct. So, this is how you can see a typical response spectrum, which was developed part of my research for to understand how the different layer velocities are getting the response. So, this is actually the input response of the given earthquake, okay, which is basically a bedrock, a engineering bedrock site, okay, rocks. So, this is like rock recorded data. So, when it undergoes a different passes through different material, okay. So, starting from this is basically a 100 meter, okay, then the 75 meter, 50 meter, 40 meter, 20 meter, 10 meter and 5 meter. You can see that the red one is basically surface. So, this time history only what we have discussed the previous slide, the time history of the that data from different earthquake. That means, you will get different time history of the data with respect to depth, as long as you have change in the material density, stiffness and Poisson ratio. If there is no change, you may get a same, only if the distance are very large you may get a difference, but otherwise for the shorter distance it will not have any change. So, you can see the surface one and then the 100 meter one, then 75 meter one, then the 50 meter one, you can see the different color actually, the 40, 20 and 10 and 5 meter depth. So, overall you can see this is actually attaining a different peak level at a different period. All of them the peak was attained only on the this range 0.1 to 1 seconds of the natural period. Just basically this is the period, not time. This is a period which is like represents a natural period of the single degree freedom system. Okay. So, you can see there is a variation. This is how you can get a response spectrum by doing a response spectrum analysis. Okay. So, you can take a time history data and convert into the, so do a like the solving that wave propagation equation by single degree freedom, you can get response, that is a typically response at a different depth. So, this response, okay, and the time history will give you the total clear picture of your particular earthquake. But in a given region, okay, you are you can expect any type of earthquake. So, as I have to mention here that, so recently there was a lot of news, okay, as on today when I am recording this video, okay, the 1st June 2020. So, there are many tremor, okay, or you can say that minor earthquakes. Okay. So, the minor earthquake reported in Delhi region in the last 2 months. Okay. So, these minor earthquakes starting from magnitude of 3, 3.5, 4, 4.5 something like that. So, people have felt, okay, there is not casualty or damage, but people have felt the NCR region, okay, in the Delhi. This is predominantly reported in the last 2 months, even though there was a shutdown and a lockdown, then lot of things are happening, but this earthquake being reported. So, as a seismologist myself and also many of the colleague, okay, who actually know about the history of the earthquake, including you have studied now how the earthquakes are occurring. So, these earthquakes, okay, it may be a foreshock. Okay. So, the foreshock is actually a smaller event which is happening before the main earthquake. Okay. So, these events may be a foreshock, there may be a big earthquake one can expect in that region. See, a big means, so it is not that it should be like a magnitude of 9, 10 kind of things. It is anything which harm a human being. Okay. It is above 5.5 and 6 which causes a damage and then hazard and disaster, those kind of earthquake we call it as a big. Okay. So, if the disaster earthquake we have said that if casualty is more than 10 people. So, these kind of earthquakes in this place it is expected. So, as on now I am talking on June 1st. So, I am not very sure when you see this class what date it will be, but you can check in case it happens during this period. So, then there is a the gap between the main shock and foreshock is very short if it happens before you see. Okay. So, in case it happens slightly longer end of this year or next year, then the gap between the foreshock and main shock is slightly larger. So, that is what you can see. So, this kind of different earthquakes can be expected in the particular place. So, those earthquakes, because when you want to design, okay, a single spectrum may not be sufficient. Okay. So, then so you have to go for the developing a design spectrum. So, I will give you a glimpse of what is mean by the design spectrum, because last class we discussed about the tripartite plot. So, this is necessary to understand what is this design spectrum also. So, the tripartite plot basically a plot of a several, okay, so median response spectrum plotted in the 3 dimensional graph. Okay. What is the 3 dimensional graph if you can see. So, this is basically a this axis is actually basically a PGA. Okay. So, then this axis so basically this is a velocity. Okay. So, the velocity values, okay, velocity versus time, and this axis will be a acceleration versus time, okay, the peak ground acceleration. So, this axis will be a displacement versus time. So, you can see a 4 axes in the single graph. Okay. In that 3 axis is actually a dependent axis, one is independent axis. So, here the time is basically a period. Okay. The period is actually a independent axis, the velocity and acceleration, and then the displacements are the dependent axis, which is a function of your time. So, you can see that same response spectrum. Okay. So, it has been plotted here, it will look like this, you can see here, see how it looks. So, this is how you beautifully get this shape. So, why we need to draw this, basically when we discussed about this time domain parameters. So, we found that basically the acceleration are very sensitive to the high frequency range, velocities are sensitive to the intermediate frequency range, and the duration sensitive to the low frequency range. So, if you do the reverse, the acceleration sensitive to the low period and velocity is intermediate period and the duration is long period. Okay. So, see, you can see that the accelerations will be almost similar, or you can make it a constant kind of values within the its sensitive region. Similarly, velocity can be made constant within their sensitive region, displacement where you can make it a constant. So, this concept has been extended to derive a design spectrum. So, if you look at a Indian code, those who study civil engineering subject, they will be come across Indian code called IS 1893. Okay. So, now the recent version is 2016. We will also elaborately discussing about this IS code in our classes when we talk about the seismic zonation of India. So, now we will only recall what is there in IS code. Actually, this is called as a design spectrum. So, the design spectrum, which is all the country will give the design spectrum. So, this design spectrum basically is a period and then spectral acceleration, then they give some shape. So, this is basically a Indian design spectrum, which is has a 3 division on this part, okay, which is for the hard rock, medium soil, and then the soft soil. Okay. So, dense medium or hard rock, medium, soft soil classification. So, this is the period, this is the SA. So, this is basically a design spectrum. Okay. So, this design spectrum, as we have seen that the low period is acceleration, this is the velocity, this is the displacement. So, in order to get this picture, one has to need to understand how this tripartite plot comes. So, basically your response spectrum data per a given site from the different earthquake data you can take, and then after getting the response at particular depth or surface level, you can basically combine all of them, and this is the like is under 200 data here. So, 100 and 200 data compile, then you take a medium. So, this medium you draw as a single line. So, this is the where you can expect a constant value. So, this is the constant value you will expect. So, when you superimpose all of them, this is basically PGA, that PGA what we have seen in time and domain, that one, this is basically a PGV and this is the PGD. So, where it interacts actually, that is depends upon the again region to region, it may not be constant to all the places. So, you will get where it interacts, okay. Then how far these values are different from this PGV, PGA and PGD, that too you can arrive, and if you arrive that, using that you can get a design spectrum. So, this is the typical design spectrum we have developed for the North India part of our research. These papers are under review. So, I do not disclose too much about the result, but just I will give you the idea of it. So, as I told that this is the medium curve. So, then that median curve, that is the median curve smoothed and averaged from the large number of response spectrum, which is plotted in the tripartite. Then I made to fit that, okay. So, by a straight line, you can see I am fitting to the straight line, then I get here this one. So, this cutoff period, okay. So, this cutoff period and value how it is different from PGA, how it is different from PGV and how is different from PGD is the factor called amplification factor, or a factor which is more than this PGV, PGD and this one. So, this PGV and PGA, PGDA also can be obtained mean value for the given data, and this is the mean value which is from the response data, which is like the variation of the PGV, okay, with respect to the PGV of the data. So, then from there you get your plot. So, that is like you, so plot this in the normal plot. So, normal graph like this. So, okay, so this is the acceleration sensitive region, velocity sensitive region, this is the displacement sensitive. So, this is called as a design spectrum. Okay, this is called as a design spectrum. So, this kind of spectrum will be obtained by through a this detailed tripartite plot. So, for your information, the currently available IS code design spectrum not developed like this, okay, which is only copied from the previous works which is carried out or elsewhere in the olden earthquake, and this spectrum does not even account a data recorded in India. Okay. So, since I do research on this, this was our observation. So, we have been working on to update this. Okay. So, maybe hopefully I will come up with the new design spectrum which is after published can recommend it to the code for which will be useful. So, this spectrum, as I said, that it is a function of your site also. If you the rock site, you will have the different shape, soil site it has a different shape, depends upon the your soil thickness and stiffness. So, this is the you can see the control period, you can see the control period and then the factors, okay, which is above these values. So, these are all the values we will be estimating using the systematic analysis of the recorded earthquake data in the same region. Why I insist a same region? As we know that India has a two type of seismotectonic setting majorly. One of them is peninsular India, which is like stable continent kind of things. The another one is the active region, which is very close to the plate boundary, like this Indo-Gangetic basin and rest of the in and around the region. This is the two major classification you can define. Even if you want to go minor level also, you can even classify the northeast part separately. So, when you are talking about the seismicity of India, we will discuss about how these regions can be divided differently in detail. Okay. Right now, I will just give you, but we have a same spectrum throughout the country. Now, you can understand how we have the spectrum when compared to the state of art knowledge available in the world. And the second, we have the variation in the soil only on this part, but actually the variation in the soil can also cause year as well as year. Okay. Both may affect, but Indian code only recommended here. So, are suggested as on now old data only for this part, but this portion, okay, will be basically western countries code as variation year as well as year. Okay. So, that is the variation you can get in the western country, but here our code. So, as on now our code design spectrums are somehow need to be updated, okay, after a proper research and understanding this one. So, as the soil spectrum at acceleration sensitive, velocity sensitive and displacement sensitives are completely different. So, the as on now, as I said that the western code are being updated version, how that spectrum looks, I will just give you the glimpse of video. I mean the drawing up that how ours and their western country code actually. So, the western country code basically, so they have one for rock like this and then the one for okay. So, this is like rock, this is soil 1, right now I call only soil 1, soil 2, something that soil 2 and soil 3. This is basically soils are with different thickness and stiffness. So, this is our modern code. So, our Indian code basically what it does basically, our Indian code is only giving like this, this one same and here they have the variation for the different category of soil. Okay, that is the difference between the modern code and Indian code in the broader variation. Okay, so, we have been working in the last 2-3 years to update this, as I told you that the present Indian code, okay, IS 1893 2016 version. So, since it is developed very beginning on 1962, from that time onwards the spectrum not changed much. This spectrum was basically copied from the previous work done in the western countries. Okay. So, this is not based on the recorded earthquake data in India. So, which we have studied, and then we understand that there is a need to develop such kind of design spectrum for Indian condition. So, what we are doing actually, we have been collecting a acceleration time history of the different available earthquake in India, and then try to characterize that earthquake data as a rock and a different soil class. So, right now since you are not studied this soil classification as a part of your course, so I just give you a glimpse of soil 1, soil 2. So, these are basically different in height of the soil, a thickness of the soil, and then a stiffness. So, this will make these classes. So, similarly rock different from this one. So, we characterize data what we collected and group them according to which category it falls. So, there is a systematic analysis and process. After grouping them, that particular time history, okay, we will take it and develop a response spectrum. From that response spectrum, we will go for the tripartite plot. Okay. So, if you have the considerable number of data on each group, you can create a mean and average and try to get a tripartite plot, which we have discussed here. So, this is the tripartite plot procedure what we have seen basically. So, this is the procedure what we have seen. So, this is what we got, and then followed by this also we got, and cutoff period we estimated. Finally, we arrived this shape, okay, which is we found that the shape and cutoff period like this control period, okay, or cutoff period, and the factors this 2.5, 1 point completely different for South India and North India, or peninsular India and active region, as the source characteristics and the site characteristics and path characteristics are completely different. So, this observation we made, actually now these papers are under communication and under review. So, once we have published that, then this spectrum will be made available to the general public. People can consider that response spectrum will be more robust way than the current response spectrum, which does not include recorded data from India. Okay. There is a message from this tripartite response plot kind. So, those kind of spectrum development is called as a design spectrum. So, as such the developing design spectrum itself a PhD topic. Okay. So, whatever I discussed the last 3 slide, okay, I was only talking about the 3 slide time history data and the response spectrum and tripartite. So, doing this for a larger area and larger data is a topic of PhD, as you will be trying to understand how the magnitude and the distance and the site condition and the source condition affecting your shape of the spectrum. Finally, which shape you recommend, why you recommend that, you will justify and give a reason. So, if you complete the entire work by 3-4 years, then it can be taken as a one of the PhD useful research for the country level improving our design practice of the earthquake engineering. Okay. So, this is very important area of topic. So, I was also surprised that when I start working on this response spectrum design spectrum about 2-3 years back, nobody was even thought about and done any work on this. There's, you can find very limited publication on developing a site specific design spectrum. Okay. So, for the Indian condition, people have done here and there some work, but there is no development of design spectrum. So, then actually maybe if we publish, okay, with a systematic data, that will be the first work. There was some work done parallelly at IIT Bhubaneswar, but there also there was some kind of limitation is there. So, anyway, this is not the place to discuss those things, but just to give you idea, like they also trying kind of this one work part of his startup project. Okay. So, one of the faculty in IIT Bhubaneswar, they have done. So, the developing design spectrum itself a PhD topic. So, which requires a lot of care and attention, as this decides your safety of the building. As I told you that there may be a future big earthquake in and around the Delhi region, because there is a foreshocks are being reported. So, if the people designed, okay, their earthquake according to the proper design spectrum, they do not even have a minor crack or something like that. So some people not even designed, they will have the disaster, collapse and failure kind of things. So the providing the useful data is one of the main contribution has to be made from the academic and research side, where we have to give a proper design spectrum to the people. We are working towards that. So hopefully in the short time of period we may have that publication, people can use that as this one. So with this basically I will close this lecture. So even though I told I will discuss about the simulation, but since it was half an hour over, so the simulation part we will continue in the next class. So we will see how we can simulate the acceleration time history of the typical earthquake. What are the simulation models are available, what is the advantage and disadvantage, okay. So what are the parameters we need to consider, that we will discuss in the next class. So thank you very much for watching this video. So I look forward to meeting you in the next class. Thank you.